Welcome back to another Bgcse past paper review. Today we're doing a physics paper. We're doing paper 2. This is from the year 2019. Again, remember, always write a school number, your candidate number, your surname, and your initials. Again, read through the instructions carefully before you start this examination. Again, please remember, do not open the booklet until you're told to do so. Now let's jump into the first question. And this question reads that the question is about common physical quantities and their units. It said, using the list of units provided, write the possible units for each of the following physical quantities. A unit may be used once or not at all. All right, so again, we're going to use these once or not at all. And so let's go into this. So write down the units for velocity, power, and so on. So let's talk about velocity here. Velocity is meters per second. So here we have it. So that one is in our highs. So it's going to meters per second. Let's go to power. So power, it is now change of energy over time, or the rate of change of energy, or it is joules per second. So let's see if we have a joules per second here. All right. No, there's no joules per second. But let me show you something real quick. To calculate joule, joule is the same thing as work. So therefore, Newton meter is the same thing as a joule. Okay, so Newton meter is the same thing as a joule, which is force times distance. That is the work done, and that is over time. So therefore, Newton meter per second is the same thing as joules per second. So for power here, it will be Newton meter per second. Okay. So power, it is Newton meter per second. Work done over time. Now momentum. Momentum, it is mass times velocity. So it is kilogram meters per second. And let's see, we have it here, right? Kilograms per meters, kilogram meters per second. So kg meters per second. All right, great. Let's go to the next question now. And this one is for mass. And mass is measuring kg. Or grams, so but the SI unit is kilograms. So let's see if we see that. Kg is there, so we are good at that one. Kilograms here, so this is kg. All right, great. Acceleration, let's go to acceleration. Acceleration is meters per second squared. Let's see if we see that. Okay, so acceleration is meters per second squared. It is right here, meters per second squared. So that is straight off the bat right there. Meters per second squared. All right, let me write in that squared for you real quick. All right, great. And now amplitude. Now amplitude is a form of distance, which is the height of the crest or the depth of the trough. So that could be in centimeters. It could be in meters. All right, so let's see if we see that it could be in millimeters as well, but anything that deals with distance, we good. Yeah, we have it right here, meters. So we could use meters to measure the amplitude, all right, of a wave. So meters is good. Density. Density is mass over volume. So therefore, it should be grams per centimeters cube or kilograms per meters cube. Let's see if we see that one. All right, kilograms per meters cube. Yes, it's right here. So kilograms per meters cube is there. Let's put that one in. So kg per meters cube. Okay, let's type in, write in that meters cube part. And then weight. Weight is in newtons. Okay, weight is measured in newtons. All right, so let's see if we see newtons here. No, we have a Newton meter, but we do not have any newtons. So now we're in a little bit of problems. So what I want you to remember now when it comes on to weight, weight is a form of force. So if we can find a formula for force, we are good. But let's remember what force is equal to. Remember that force is equal to mass. So force is equal to mass times acceleration, right? Remember that? Force is equal to mass times acceleration. Now remember that mass, again, is kilograms. So we can put mass is measured in kilograms. Let's put kg right here. And acceleration is measured in meters per second squared. Okay, so acceleration is meters per second squared. So now let's look carefully now. If you could put kilograms, meters per second squared together, then that should give us our formula for our weight, because weight is a form of force. So let's see now if we do have that. Kilograms, yeah, which is right here, kilograms, meter per second squared. So that is our answer right here. So weight is also kilograms per, kilograms meter per second squared. Let's write that piece in. The squared. All right, great. All right, now we could move on to the next question. Now the next question now reads that calculate the acceleration of a car traveling at a velocity of 20 meters per second and comes to a stop in 25 seconds. Now, there are certain things you need to know. First, we have our velocity right here, which is 20 meters per second. Very important to note that the car is coming to a what? Stop. So the car is stopping. That is a very important thing when it comes on to motion question. If you see stopping, something must come to your mind. That means the car is decelerating. Okay, just bear that in mind. So you ask us to calculate acceleration. So if the car is accelerating, but again coming to a stop, is actually termed as deceleration. But you would have known that acceleration, right, is equal to velocity over time. Okay. And so we could calculate velocity over time by saying our velocity, which is 20, okay, divided by time, which is 2.5. And so this gives us 8 meters per second square. So let's put our squared symbol there. Okay. But what is important here now is that we need to remember that as again the car was what? Coming to a stop. So therefore, we can have this here. Let me just erase that. That's not looking too nice. Okay, let me just put it properly for you. Okay, so therefore, we can say, okay, since the car is decelerating or coming to a stop, then acceleration will have a negative value. So therefore, the acceleration, right, will become a negative value, and so it becomes minus 8 meters per second squared. Okay, so that will be now our answer there. All right. Okay, let me just quickly put my equal sign up here. I never put that. I forget that. Okay. All right, so great. So that will be our answer. Negative 8 meters per second squared. That is the acceleration in negative value because the car is stopping. All right, this question is out. I'm very glad for that. Let's go to question number 2. And this is a pulley system shown right here. We have effort, we have weight, we have 4 meters going up. Let's see what the question asking. It's an object of weight 100 Newton is being lifted using a simple machine. All right, so that simple machine there is a pulley. So give the name of this simple machine. So this is a pulley. All right, so that is a pulley. That's the name of that simple machine. It is a pulley. Now let's go to the next part of the question right here. Now, and this part of the question, it reads that calculate the mass of the object using G equal to 9.8 meters per second squared. And so to find mass, again, you need to have the weight. So if we, because matter of fact, just remember this formula, maybe it will help you out a little bit. Weight is equal to mass times gravity. Okay. And so to find the mass is going to be weight divided by gravity. Okay. So let's look for our, matter of fact, input G here. So G is equal to the weight. We want to find mass. Mass is equal to the weight divided by gravity. Okay. And so let's look what our weight is. Our weight is 100 newtons. Okay. And our gravity is 9.8. So therefore here our mass now is equal to our weight, which is 100 newtons divided by 9.8, and that will give us here 10.2. Okay, 10.2. All right, so now we have that is out, and this is in kilograms, just to make note of that. This is in kilograms. All right, excellent. Let's go to part C. In part C, it said, what is the gain of gravitational potential energy of the object if it is lifted 4 meters? So if you're lifting the object 4 meters, what you need to know, all right, is that to find gravitational potential energy, which is, let's say PE, the potential energy, this is equal to mass times gravity times what? Height. Okay, that's the most important thing to remember. So mass times gravity times height. And so what is our mass? We calculated it to be 10.2 up top right there. So it'll be 10.2 is our mass, multiplied by the gravity, which is 9.8. Okay. And it moves across a height of 4 meters. So we're going to multiply that by 4 meters. So height is 4 meters. And so this will give us 399.84 and this is energy, so this is in joules. Okay, so that's very important right there. I'm going to show you something here that you could do as an alternative measure to in terms of calculating this thing. So I want to show you something here. You don't need to go through this, but I just want to show you just in case. Mg, remember mg, mass times gravity is weight, right? Remember it? Mass times gravity up here is weight. So mass times gravity is weight. Okay. And so if we know the weight of the object, remember the weight is given in the diagram. Let's show you what I'm talking about. The weight here is 100 Newton. Okay. That's the weight, 100 Newton. So therefore I could put my mg to be 100 Newton, right? And my height will be 4. So I could multiply 100 by 4. What do I get here is 400 joules. Okay, 400 joules. Okay. Now, what's the difference between the 400 joules and the 399.84? Because this was calculated from the calculated mass. And because we round off to two decimal places, then that's why this is not exactly 400, right? But I just want to show you this cool way to do to find energy as well. The force or the weight times the height is the same thing as saying mgh, okay? All right, because mass times gravity is the same thing as weight. All right, cool. Now, since we have that now, again, this also shows some extra stuff, right? There's nothing to it really. All right, just help you out a little bit. All right, so let's go to the next question here. It says, state the velocity ratio of the machine. State it. There's no need to calculate it. And so let's go to the Pulley system. I'm going to show you something that you need to know. When you talk about the velocity ratio, right, it's also called a distance ratio as well. But what I want to point out right here, is that for the fact that you have three lines, I'm going to show you them, right? They will move technically equal distances, all right? And so we have these 3 lines here. So therefore, we know that our velocity ratio will be 3 because there's only one line right here, right? And so the effort will have to move 3 times. The effort will have to move 3 times as much as the distance as the load itself, right? So therefore, again, because of further movement in terms of distance, 3 times in terms of ratio, then we know our velocity ratio is 3. Okay, and so 3 distance by the effort and 1 by the load. All right, and so here it is equivalent to 3. The velocity ratio is equal to 3. Okay, and just remember what velocity ratio is. I could really type in that for you right here, what velocity ratio is, just for you to remember it. So velocity ratio, let's call it VR. Let's say it VR. Okay. VR. All right, let me just put it in uppercase. VR. So velocity ratio is equal to the ratio. Okay, is the ratio of the distance Okay, moved by the effort. So moved by the effort. Okay, moved by the effort. Okay, and the load. Move by the effort and the load, okay, within the same time period, okay, within the same time period. All right, so that's what it is. So they're moving at the same time. All right, let's pick a space between that. Okay, so they're moving at the same time. And so it's a ratio between the distance moved by the effort versus that of the load within the same given time. All right, so that's what we call velocity ratio. Let's jump into this part of the question here. So calculate the distance moved by the effort. The distance moved by the effort, we need to note that because I'm going to show you something real quick again. Based on the definition I tell you just now, you have to use the velocity ratio right, to actually calculate that. So what I wanted to understand here, all right, I'm gonna give you a quick formula. So this is the velocity ratio, which is 3. The distance moved by the load is 4. So without calculation, if the ratio is 3 to 1, you can actually know what that is, right? 3 times that, 3 times 4, that will be the answer. But let me show you the calculation or the formula for this. So going to be velocity ratio. I'm just putting a big R right there. Normally put a big V with a small r, subscript R. All right, but just in terms of calculation, this is the distance moved by effort. So the effort distance. So the effort distance. Okay, so the effort distance, let's put it like that, divided by the load distance, or the distance moved by the load. Okay, so I just want to kind of see that. All right, so that is the formula for velocity ratio. But what we want to calculate is the effort distance, the distance moved by the effort. So all we need to make is effort be the subject of the formula. We could use E and L. And so we want to make the effort be the subject of the formula. So therefore it's equal to velocity ratio times the distance moved by the load. And so therefore our effort distance here, okay, our effort distance, all right, will equal to our velocity ratio, which is 3, multiplied by the distance moved by the load, which is 4, which give us what? 12. That was in meters, I think, yeah. So meters. All right, so let's just check if it is in meters. I think it's meters. Oh, yes, it's meters. Okay, great. All right, so yeah, so it's 12 meters. For part F, here it asks us now to calculate the mechanical advantage of the machine. And so mechanical advantage, now let's give you a quick formula there. Mechanical advantage is equal to load over effort, right? So this one is equal to load divided by effort. Okay, so load divided by effort. And so the load, as we calculate the load up top there, it was 100 newtons was the load. And let's go back to the effort. And so the effort here, it will be, let's see if we did calculate that. All right. All right, 40 Newton. The effort is 40. Okay, so great. We don't even need to calculate nothing. It was there on the diagram. So 40 and 100. So it will be 100 over 40. All right, so the load over the effort is the mechanical advantage. So divide that by 40. All right, and so that equals to 2.5. The mechanical advantage is 2.5. And so therefore you can lift, in other words, if you use this pulley, you can lift something 2.5 times greater than the effort that you put in. Okay, that's what it's saying. Now now it asks us to calculate. It's using the answer from C and E. Calculate the efficiency of the machine. All right, so efficiency of the machine can be given as 2 different formulas, right? And they ask us to use C and E to do that. So E was, let me just see what is in E again. E is the distance moved by the effort. Okay, and in C, we calculated the energy right here. Okay, all right, so we're going to use something here to see what's going on here. All right, so I'm going to give you 2 formulas to find efficiency of the machine where this is concerned. You can use the efficiency of the machine. Okay, let's say efficiency is equal to the mechanical advantage. So going to be the mechanical advantage. I'm going to put MA. Just please remember what that is. Mechanical advantage divided by the velocity ratio. So I'm going to put VR right there. Okay, so remember what VR is, velocity ratio. I'm just doing this for short. Normally put a small r as well. All right, so now we establish that, and this is going to be multiplied by 100. So because I do this form, I'm going to put the times 100 in up here, times 100 right here. This is 100%, a matter of fact. All right, all divided by VR. All right, or let me make this even more clear because I really don't want to confuse you at all. So I'm gonna take this out, okay, and just say, put this here. I'm gonna put it as a proper fraction, so I want to see it properly. So it's mechanical advantage divided by velocity ratio. Okay, so VR divided by VR. All right, just wanted to note that. All right, and then now I put my line to say these are dividing by, because I really want you to see this properly and without any form of confusion. So this is one way which you could calculate efficiency. Another way you could calculate efficiency is by saying that efficiency, all right, I'm going to write EFF, right? Just for short. Please just remember that it's efficiency. All right, I really want to finish this real quick. And so efficiency is equal to work. So equal to work done on the load. So work on the load, okay, over work by the effort multiplied by 100. Because again, it's a percentage of percentage efficient the machine is, and divided by the work by the effort. Okay, so just want to note that. All right, so this is another formula you could use right here. So let's just say divide by here. Okay, I'm gonna divide. Okay, all right, so great. So that's two formulas there. So we could plug any information here and we could work it out real quick. So let's say I'm using this formula to say mechanical advantage times 100 over velocity ratio. We know a mechanical advantage. Let's go back to it a little bit right here. Well, mechanical advantage is 2.5 right here. So it'd be, so this could equal to 2.5, right? Times 100, okay? Okay. All divided by velocity ratio. And our velocity ratio, remember, it is 3. So you can just say divided by 3, okay? All right, so divided by 3. All right, let me put it here. All right, so divided by 3. All right, and this will give us here now, so this will be 2.5 times 100 divided by 3. This will give us here 83%. So this will be 83%. Yep. Let's see if it works out for this as well. Let's put the equal sign right here. So this equal to, oh, wrong place. Okay, let's put it right here. Come on, come on. Great. All right, so equal to 83%. Let's see if the second formula work out as well, right? Work done on load over work done by effort. So what is the work done by load? Is simply the force times the distance. And let's go back to the diagram and show you something real quick, right? So the effort, the load here is 100 Newton and the distance moved by it was 4. The effort is 40 and the distance moved was 12 because remember the mechanical, the velocity ratio is 3. So the distance moved by the effort is 12. Okay, so let's see now how we're going to work this out. So this will be here for this one. Work, let's put it underneath right here. So the work done by the load would be the 100 newtons, right? Multiplied by the distance by the load, which is 4. Okay. All multiplied by 100. So you can just say multiply by 100 one time. And we're going to divide all of this now by the work on the effort. And the effort was thus 40 newtons. Okay. Multiplied now by the distance moved by that is 12. And then if you should calculate all of this, what you'll get on top there, it will be 400, all right, times 100, right, over 40 times 12, okay? You could get here, let me just do this a shorter way here. All right, so we'll get 400, let's do it like this, 400, okay? And then, or I could simply just put 40,000 right there. I could just do that as well, 40,000, let's just do that. 40,000 over 480, over 480. And if that is over 480, then this will equal to, again, 83%. So it works out. Yep, 83%. All right, so both formulas do check out, okay, for us. All right, again, you can use any one. But again, based on what they asked, though, the second one will be most appropriate because there's a use from C and E. So I guess this one will be the best one to use. All right, so let's go up. I just want to go a little bit up top again to just remind you about the calculations there. All right, so those are the calculations for efficiency. All right, again, mechanical advantage, okay, over velocity ratio times 100%, or work done on load over work done by effort times 100%. And we're good to go in terms of our efficiency of the machine. Let's go to the next question here. Our next part of the question. No, this question finished. Wow, this is number 3. All right, we are on a roll today. Now, this question is on electromagnetic magnetism. And here it said that figure 3.1 shows a simple electromagnetic relay. Okay. And we have a circuit P, we have a circuit Q. All right. And so circuit P, circuit Q. And here now it said that on figure 3.1, indicate the direction of the convectional current on the circuit P. So on circuit P, we want to talk about convectional current. And so let's put this, oh, I'm gone too far. All right, so the convectional current, you will see the current flowing from the positive. So the longer, in the battery, the longer piece is the positive. So it flow from the positive into the negative. Okay, so that's for convectional current. Convectional current flows like that. All right, so we could, yeah, motherfucker, you could label this. You need to label it. Once you do it, please label it. Yes, please label. Even though they're going to look for the your arrows and so on, but labeling to tell them that, okay, this is exactly what you're talking about. So this will be our convectional current. Let me just write our conventional current right here. Okay. Our current. All right, so that will be it. So I'll label that piece here. So conventional current would be that. All right, and so the next thing they ask us to do again is after conventional current, they ask us to now show the direction here. No, the magnetic field pattern around the solenoid, the current flowing, and they said the current is flowing counterclockwise when viewed from the left end of the solenoid. And so again, you want to put what is happening here, just to point out real quick. Let's put this in a different color, right? I'll put this in blue, so I don't want this to be confused with anything else. But the fact now, what is going to happen here is that coming in here, what you need to know, that in terms of conventional current will help us in terms of the direction of the magnetic field as well. Okay, if you remember, for example, Fleming's unruled, okay? So we know the field, yeah? So if the current is coming this way, the field will come this way. So these, the field will drop down like this. So these are small arrows will be your field, the direction of the magnetic field right there. Okay, let's put them on. All right, I'm putting on all the wires. Okay, so the field will look like that. And then this will eventually goes up like that, right? So just to show you what's happening there. All right, and so the field is, you know, going like that, technically. All right, so great. Now, point to note, again, I'm going to draw next line right here. I'm going to show you why I'm going to do this. Because, again, we need to know our poles, all right? And coming from the positive end, you'll get your north pole. So I'm putting N right here, north. This will be your north pole right here, all right? And this will be your south pole. And the reason I put these arrows is because, remember, the magnetic field will flow from the north into the south. Just remember that, okay? Okay, great. That is now covered. The next part here that they asked us to do, oh, come on. The next part they asked us to do right here, let me see if I could get that piece in. Take these two things out. All right. So let's go to the next thing they asked us to do. I think they asked us to do something here. Part 3, yes. The polarity of the solenoid. Oh, I just put them in. Okay, so it's north and south pole. So that is great. We covered that as well. Awesome. All right. So we have covered that. Now for part B, it's a state 2 factors, right? That would increase the strength of the electromagnet shown in the circuit. And remember, I think I've discussed this. I'm not sure if it's combined science or physics, but I've discussed this before. And the two things that will increase the strength of an electromagnet is, one is to increase the current. So if you increase the current, yes, the strength will increase. And also if you increase the turnings, so increase number of turns is also another option right here. So increase the number of turns, okay? The number of turns, okay? All right, great. All right, and this is the turns in the solenoid, a matter of fact. All right, so that's good for that. And so there's a next part of question. I think there's a next part of question. Let's jump into that piece real quick. All right. you know, I could go back to something here. Okay, all right, let's go to the next part question. I was going to show you something in a diagram, but I'll show you if I need to do that. All right, part C is what should happen to circuit Q when the switch in circuit P is closed. So if you close the switch in circuit P, all right, let me point this out. If the switch is closed in circuit P, which now means the circuit is now on. So let me put this in a color right here. Green is good. So now this is closed. That means current could flow straight through the entire circuit now. Okay. And if current is flowing through that, then this will magnetize because of the flow of current through it, because they create a magnetic field. And so the soft ion will go inwards, okay, inside of the solenoid, because it will be attracted, the metal iron core. And so iron will attract the magnet. So once that magnetic field is created, the iron will go inside of the solenoid. All right. And once it go in the solenoid, this end right here, because of the shape of it, will push these two together. So you push the top one down to the bottom one and they connect. And so this circuit right here now will be closed. And if the circuit is closed, then current could flow through the circuit and this light will be on. Okay, that will be on. All right, so great. So that's what happened here. Let's try put that in some words here. All right. Put that in some words. All right, so great. Now it said that current will flow into so circuit. So let's put it this way. Circuit Q, which is the second circuit. Okay, so circuit Q, all right, will close. Okay, so will close and the light will be on. Okay, and the light will be on. All right, so that will be your 1 point answer. Or simply, the light will come on. The light will be on. So why does this occur? All right, all that I explained to you just now, we'll have to put right here, right? So let's see if I could put them in real quick. All right, so first thing that happened here, as I mentioned, the solenoid, right? Because of the flow of electricity through the solenoid, okay, the solenoid becomes magnetized. Okay, the solenoid becomes magnetized. All right. All right, so become magnetized. All right, and once become magnetized, all right, what will happen here now is that the solenoid become magnetized and the soft iron core, okay, and the soft iron core or iron or soft iron, okay, will now pull or be pulled into it. Okay, the soft iron will be pulled. Oh, I want this all the way over here. Will be pulled inwards. They're causing the spring contact, because there's a spring contact they use right. They have a switch. They're causing the spring contact to close. Okay, causing the spring contact to close, resulting in the flow of current. Okay, yeah, the flow of current. All right, great. So that's what happened there for the light to be on. Again, when the P circuit is closed, then definitely what will happen as a result is that the soft iron, because it's metallic, it will be pulled in that magnetic field. And once it pulled in that magnetic field, what will happen next is that you turn on the next circuit with the circuit Q. Okay. And once circuit Q is turned on, then definitely the bulb will be on at that time. Okay. All right. So great. All right. So now we have that covered. Let's go to the next question right here, which is part 3 of this question. And say, give one use of electromagnetic relays. Electromagnetic relays can use a number of devices. As a matter of fact, a lot of devices now, especially in automobiles, contain relays. So the relays are a lot of relays in cars now. So the alarm system generally could, alarm systems, they could use relay as well. Okay. Car horns, the horn in the car could also have a relay system. All right, and again, there are a number of things you can have application for, especially in cars. Most of the systems are controlled by relays, as a matter of fact. Electric fuel pump is a good one. Electric fuel pump. They use relay system. All right, and so you notice that sometimes when the pipe is on, you could hear the pump come on, then trips on, because it is on and off based on pressure. So pressure will cause the pump to come on. So based on that will be the switch. Okay. All right. So great. And again, it is magnetized to come on, come off, come on, come off based on pressure. All right. So those are some of the basic application. Again, practical one that most person will know is electrical fuel pump, or I could say water pump as well. I say fuel. It could be also water pump, fuel or water pump. So that's the next one too. Water pump uses that as well. So I can put water pump. I was explaining water pump or fuel pump. Yeah, I have water in my mind, but I have fuel. But fuel pump also use the same thing. All right, great. Let's go to question number 4. We're halfway there, yes? We're halfway there. All right, so this now, and this reminds me of the paper one that I did earlier. It said that the table below shows some information about electromagnetic spectrum. Here we have radio waves, we have a missing one, we have infrared, we have visible light, we have missing one again, we have gamma ray, we have X-ray and then gamma ray. And then it asks us now to name radiation A, and remember that this is microwave. Okay, so microwave is close to infrared, and they could use for applying heat to food. Okay, so microwaves. All right. All right, and so for B and B, the missing one there, it will be ultraviolet radiation or light. Okay, so this ultra. Okay, violet. All right, so ultraviolet rays. Okay, ultraviolet rays. All right, so great. So there we have it. And again, remember that I'm going this way from the radio waves going on to gamma rays. The wavelength decrease. Okay, the wavelength will decrease. All right, just remember that. Now it's a state 1 use of X-ray. X-ray can be used for a number of things. Generally, X-ray is used for scanning. It's generally is used for scanning, right? So, well, what is used for scanning is really part of the body. So that's a basic use for X-rays. You get a broken bone, you go to the doctor for a scan, X-ray scan. So it is scan the body, okay, or to scan and view. Okay, so scan and view. Scan and view the view parts of the body. Okay, parts of the body, such as your bones and so on. All right, they could take an X-ray of your lungs. Different parts of the body could be X-rayed for different things. So they want to scan it, they want to view it. All right, so that's one use of it. All right, and state 1 harmful effect of X-rays on living organisms. And definitely this could lead to cancer. All right, especially long exposure to these things, definitely so. Part B is a state 1 property that all electromagnetic waves have in common. And so they have a number of things in common, all right? So I must give you probably two. And so one that they do, they travel in a vacuum. Okay, they can travel in vacuum. Okay. All right. And next one is that which is common to all of them. They are transverse waves, so they are transverse in terms of property. Okay, so they are transverse. Okay, that's another one. And I'll give you one more is that they travel at the speed of light. They travel at the speed of light. Okay, so travel, okay, as the same speed or with the same speed. Let's say travel with the same speed, right, as light. Okay. All right, so great. So those are 3 properties right there. All right, let's look at part C now. For part C, the diagram shows shows wavefronts in water waves approaching a barrier. The wavelength of the waves is 2.0 centimeters. I want to highlight this. So here we have 2.0 centimeters. It said the barrier has a gap of 1.8. So there's something that you need to know about right here. All right. It said now complete the diagram to show the diffraction wave fronts After passing through the gaps, draw 4 wave fronts. So first thing I want to tell you now, right? If the gap is smaller than the wavelength, then what will happen here is that they will bend a lot. There's a lot of bending taking place. If the gap is wider than the wavelength, then little to no bending will take place. All right, or you have less bending, I should say. Not, I can't say little to no, but less bending. All right, because some bending will take place once you have a gap. Now, so drawing 4 of them, let's start with very close to the opening. You have a small one, really, really curved. And then the other one a little bit bigger. All right, and of course, they won't be as curved as the previous, but they're still really curved because the fact that, as I mentioned, if the gap is smaller than the wavelength, then a lot of bending will take place. Okay, just to point that out. All right, so let's go to the next part of the question now. And this part of the question here, it said draw 4 waterfronts of wavelength 1.2 after it has passed through the gap. Now we're working with 1.2. Remember, it was 1.8. The gap was 1.8, right? So in this time now, the gap is bigger than the wavelength. Okay? So if the gap is larger than the wavelength, now as again, the opposite is true, is that now the gaps will be, the wave fronts will not bend as much as the previous, because again, bigger gaps, if the gap is bigger than wavelength, the wave fronts will not bend as much. So we can draw them like this, pretty much, not too much bending taking place. So I want to just draw them slight bending at the ends. All right, that top one a little bit too straight, but let me draw a straight line first, and then I see if I could curve the ends a little bit. Yeah, but something like that. I get the drift. Not too much of a bending taking place. Right, that one is a little better now. All right, so come on. All right, great. No, I'm getting it. I'm getting it. I'm getting it. Yeah, don't mind my bad drawings. You're gonna be nice drawings in the exam, but the fact that you're not gonna see a lot of bending take place, that's the idea. All right, the bending will not be as great as the one before. The first one is really curved. Yeah, this one is bending less, and so they're looking out for that concept. Now, part E now of this question is state that give one conclusion that can be drawn from your observation in part C and D. So what can you say about these things? All right, so firstly, to point out that if the gap is larger or bigger, if the gap is larger than the wavelength, if the gap is larger than the wavelength, than the wavelength, right? And the wavelength, there will be less bending, okay, less bending, all right, of the wave fronts. All right, so very important. So again, if you just look back on this real quick, you're going to see here again, for the gap is wider than the wavelength, so this is a shorter wavelength compared to the gap, less bending taking place. But the one before that, again, if the wavelength is bigger than the gap, then you have more bending taking place. Okay. All right. So great. All right. So that's one thing we need to have right there. And again, so that means the gap and wavelength, if they kind of, as I said, inverse in terms of production of bending. Okay. Bigger gaps in terms of if the gap is bigger than wavelength, less bending. All right. Cool. Now let's jump to the next question here. Again, moving on really fast. I really want to move fast to finish this. All right, now question number 5. And this question is about Hooke's law. Okay, so this question is about Hooke's law. Here we have figure 5.1 shows a spiral spring whose unstretched length is 0.1 meters. So this unstretched spring is 0.1 meter. That is a normal length of the spring without anything on it. Okay, all right. So now we know that it's a student then hangs objects of different masses from the spring figure 5.2 shows the spring when 1.5 Newton weight and an unknown weight W are respectively hung from it. So in one case here we have a 1.5 Newton, and in the next case here we have W. Yes? All right. So remember now, let me just put this right here, right? Because we're not going to use this. The unstretched thing was 1 meter. That's what they said, right? 1. Yep. Let me go back to it. I want to make sure. 1 meter. Oh, I'm gone too far. Oh, 0.1 meter. Okay. 0.1 meters. All right, let me just erase all of this. So the unstretched spring is 0.1 meters. All right, just to make a note of that. All right, I'll type that in. So here is the unstretched. So is it, I'm going to call this the spring length. Okay, just to, so we can be clear with this. Okay, the spring length is equal to 0.1. I just want to remind us about this, right? All right, so going to help us a little bit. And so here now, let's go down to it. It's a by how much is the spring extended when 1.5 Newton was on it. Now remember now, let's go on it, right? This is 0.1 meter, okay? So when you put 15, or sorry, not 15, 1.5 Newton on the spring, the entire spring length is 0.3 meters. But remember that the spring itself has a length of 0.1 meter, right? So therefore, by how much? It said by how much. It never asks the total length of the thing right here. It said by how much. So we want to know now that it moves to 0.3. So we're going to say 0.3 here. 0.3 minus the original length of the spring, which is 0.1, right? 0.1. And so that is extended only by 0.2 meters, yeah? 0.2 meters. That's the only way to extend. That's the amount to extend by. All right, so now that's covered. Let's see what they're asking us to do now. They say calculate the weight required per meter of extension. All right, so let's think about this thing carefully. They want us to calculate the weight required per meter. Let me just show you something real fast, right? Weight per meter is Newton per meter, isn't it? Because remember that per means divided by, right? Okay, we established that. So in other words, we're talking about the force over the extension. Yeah? Force over extension. Now, what formula gives us this force over extension? Do you remember this formula? That force, right, on a spring is equal to the constant multiplied by extension. So if you divide the force by the extension, what you get is a constant. So what they ask us to calculate, right, is a constant, really. So they ask us to calculate the constant. So we can say E now, which is constant, divided. So it'll be force over the extension. So if you write this out, let me just put it as a formula for you first, then I work it out. So force divided by extension, that's a formula. No, I'm doing something wrong. K, which is a constant, yep, equal to the force divided by the extension, that's the constant. And so let's plug our formula units into this now. So K, which is a constant here, equals to the force. All right, let's think about the force that was used right here. What force was used to pull this extension, right? Let's go for it. The force that makes this extension here is 1.5 Newton, right? And that 1.5 Newton makes an extension of 0.2. So for 1.5 Newton force, it extends 0.2 meters, 0.2 meters. So 1.5 divided by 0.2 will give us now 7.5 Newton per meter. Okay, Newton per meter. And that is our spring constant. Okay, so we just calculate our spring constant just now. Knowing the spring constant makes life easier to calculate either force or missing extension, right? So you can make it be the subject of a formula, you can transpose, you can do a number of things. Now, for part 3, it's calculate the weight, which is caused the spring length to be 0.55 meters. So now, so life becomes easy, right? It said we will calculate now, we will calculate the weight which caused the spring length to be 0.55 meters. So watch this now. The entire spring length, Matter of fact, let me highlight this. The entire spring length they're talking about right here is 0.55 meters. But you need to remember that the spring itself has an original length of 0.1 meter. So what is the extension right here? The extension has to be now the entire spring length that they're talking about right here. The entire spring length, which is 0.55. So 0.55 is a spring length. We're going to minus now our 0.1 from that, because remember the original length of a spring is 0.1. So the true extension here is 0.45, yeah, 0.45 meters. That is the exact extension. But we want to find out what weight will cause this extension, because they want us to find weight. What weight will cause the extension of 0.45? That's on the next way to say it. So instead of saying cause the spring length to be 0.55, we're looking for the extension. We're not going to use the entire spring length in the calculation, we use the extension, isn't it? So let's now calculate the weight. Remember the formula now, we say force equal to constant times the extension, right? So force is the same thing as weight. So force is equal to our constant multiplied by extension. Well, you know our constant. Let's go back to it to remind you what the constant is. Our constant that we calculate here is 7.5. Okay, let's go down to that. So we're going to say now 7.5. All right. So we're going to say, let's put F, force. So force is equal to 7.5 as our extension, as our constant, multiply by our extension, which is 0.45. And so all of this now equals to now 3.375. Great. 3.375 newtons. Okay. Newtons. Great. So that is now our answer right there. Let's go to part B. And for part B, it said, in a further experiment, the student applied similar weights to two different spiral springs. Figure 5.3 is a force extension comparative graph of the results obtained when the two springs were stretched. All right, so let's go to the graph and see what's going on right here now. So let's stop right there. So we have the force right here, we have the extension right here, right? And so look carefully. Notice how they're extending. All right, this one actually curve at the end right here. That's kind of cool. All right, so we're going to talk about say the question now. So it's use the graph to calculate the difference in extension of the two springs when a load of 30 Newton is applied to each spring. So what do we want to calculate the difference between? Difference in extension. Let's highlight that. We want to find the difference in extension when both spring was extended by 30 newtons, right? When 30 newton was applied to each of the spring. So let's go to the graph now and see how we could determine this. Okay, let's stop right there. Let's go with spring 1. 30 newtons, let's go straight across. So follow me now, straight across. And again, my hands are not so straight, yes? Okay, cool. They come in right here. All right, excellent. That's where 30 reached that line. All right, great. Excellent, that's 40. No, that's not even 40. Let's go back again. That's not 40. That's not 40 at all. All right, I take piece out. That's not 40. Let's go back. I'm going to take time with this line. I should zoom into this a little bit now. Let me zoom into this and so you get to see it better. So I want to make sure that I'm not missing. Oh, yes, better now. Great. So I'm going to come back to this line again and notice exactly where it stopped. I'm on this 30 line right here. So the 30 line is actually right here. It stopped one before the 40. So you're going to come down right here. The one line before the 40. Okay, great. All right, good. So let's establish this number now. This is 25 right here, right? So there are 10 lines between each, 10 lines between the numbers, and the number is only increased by 10. So each of them is actually, so this will be 25, 26, 27, 28, 29. No, this is 30 in the middle right here. So 30. So this will be 30. Okay. Because it's 20, the 30 in the exact middle. And if 30 is there, then each line is by 2. So it'll be 32, 34, 36, 38. So this is 38. So this line here is 38. I'm going to try to write it on. Okay. This line is 38. All right. Let's now see if I could change a different color now. and see if I could get a next line on spring 2. Let's use blue. The 30 will come over, so I don't need to really draw it from the start again. The 30 will continue over to spring 2. They stop right here. This is dead on this line, yeah? And so if dead on this line, let's go in the middle right here. And between 40 and 60 is 50. So this is 50 now, right? Cool. All right, that's 50. Not SO, okay? That's 50, okay? Please bear with me. All right, so let's now go into the calculation thing now. They want to know the difference between these two things, right? So the difference between the two extensions, one is 50, one is 38. So spring 2 goes out to 50. So we're going to say difference between is 50 minus 38, right? And so 50 minus 38, what you get as a result here is 12, and that extension is millimeter. So yes, it's 12 millimeter is the difference between the two of them when a load of 30 Newton is applied to each spring. Okay, great. Now, it said what spring is easier to extend? What spring is easier to extend? What that means, you know, is that if you apply a small force on it, if a small force is applied on the spring, it gives a greater extension. And this tells us this. Look at the 30 situation right here. 30 only extends spring 1 to 38. 30 extend spring 2 to 50. That means spring 2 is easier to extend. Makes sense, right? All right, cool. All right, let's put that in now. So this is for spring 2. Okay, that's for spring 2. Great. Now we say which spring has a higher force per meter of extension. So greater force per meter per extension means that it is more difficult to extend, because for every force requires for every meter of extension requires a greater force. That's what they're actually saying. So spring 1 is harder to extend. That's the next way to say it. Which one is harder to extend or to create a difference in length? And that is spring 1. Spring 1 is difficult. Yes, spring 1 is difficult. All right, now let's go to part 4 now. For part 4, it said, in which spring is the elastic limit exceeded? So let's go back to the graph to see what's going on here. For spring 1 is a nice and straight line, so that is great. But for spring 2, somewhere right off here, the spring starts to bend. That means spring 2 reaches elastic limit, where the proportional is no longer the same. The proportionality between force and extension is now changed. In other words, not following Hooke's law anymore. So here now it is spring 2. Okay, spring 2 past its elastic limit. It starts to deform. All right, great. That question is over. You see where we are now. Let me go back into Zoom and see if I could get back this question here. All right, that's perfect right there. Great. All right, so this question about force, weight, and mass. This is supposed to be a nice one. Force, weight, and mass is one of the basic topics that I've done from the early part of the course. So it shouldn't be that bad, right? All right, let's see what we can do real quick with this one. So we have 2 more questions to go. All right, so figure 6.1 is a graph which shows a weight change with mass on 2 planets X and Y, right? So here now we have planet X and planet Y, okay? And we have the changes here from 200, 400, 600, 800, and so on. All right, and then here now we have on the x-axis we have 40, 80, 120, 160. All right, so those are the labelings. All right, so we have force, which is weight, and we have mass. All right, so let's talk about what's happening here. So find the gradient of the line for the graph plotted for planet X. So let's find the gradient for planet X. And so what gradient equals to, just remember what gradient is equal to, right? So when you want to find gradient, is always the change of y over change of x. Now remember now, some people used to talk about rise over run, but we don't like that rise over run situation. All right, we like change of y over change of x. Okay, so change of y, so you can use it as this change. I need a triangle. So let me just take this out. It's supposed to be a triangle thing. My hands are not so good. Yeah, but make sure you get these things proper in exam, right? So a triangle, which means change. So we're going to have change in y, okay, over a change in x. All right, I'm getting the hang of this now. All right, great. Or you can have it as y1, y2, I should say. I thought I had this thing. All right, So y2, right? So y2 minus y1, okay, all over x2 minus x1. Okay, so that's the next formula right here. I'm taking up all my space, but we're going to get through to it. Minus x1. I'm going to put the numbers in, it's going to make it easier anyways. All right, so we can also now look at the gradient. So let's go back to our graph and find our gradient now of planet X. So we want to use the largest possible line. So for planet X, we could use all of this time. We could start from 0 for the y-axis and end at 800 right here. So that's our change of y, 800 and 0. And for x-axis, we could start from 0 and end at 80, which is good. All right, so remember now, 0 to 800, 0 to 80. The entire line we're using, we can use this too, but small gradient we don't do like that again. We like to use most of the lines, just in case if there's any errors in the line, we can pick them up in our calculation, right? Our gradient will kind of help us with that. All right. So let's do the calculation real quick. So here now we're going to have 800, okay, minus 0, okay, which is a change of y, okay, divided by 80, which is on the x-axis, minus 0, okay, and this will give us 800 over 80, which will give us 10. So this is 10 Newton per kilograms, okay, because the y-axis is in Newton, which is force, and the x-axis is in kilograms, so it's going to be kg, okay, so it's 10 Newtons per kilograms. All right, great. Now, the next part of the question here is part 2 now. Part 2 said, what does this value represent? And the value represents just by the mere fact that we have Newton per kilograms, right? Newtons per kg. It is telling us that is the force per mass, which is gravitational force. So this is the force of gravity. So this is gravitational force. Okay? Gravitational force, yeah? Okay? All right, good. So that's gravitational force. Let's see what we can have here now. For part 3, it's a planet X found in one of our solar system. And we have an idea what is that. It's a named planet X found in one of our solar system. Found in our solar system. All right, so here now, planet X, if it has a gravitational field of 10 Newtons per kilogram, everybody will know that now. Remember, we normally say use 10 for gravity. For what? Calculation. Anything on Earth, isn't it? So yes, this is Earth. This is Earth. This is where we all live. Well, at least for now. All right. Part 4 is an object P which weighs 800 Newton on planet X is taken to planet Y. Determine the mass of planet P. No, determine the mass of object P on planet X and also on planet Y. So again, the weight is 800 Newtons, right? We're going to calculate the weight on planet X. We could do that easily, right? The mass, we can calculate the mass. I'm saying weight. So we're going to find the mass right here on planet P of object P on planet X. I'm trying to go too fast. Let me slow down a little bit. All right, so we're going to find it on planet X. So we have the weight, and we're going to find mass. It's going to be weight divided by gravity, right? So on planet X, we have our gravity here on planet X to be 10 Newton per kilograms, because we established that this tells us the gravitational force, and it's on planet X, okay? So the gravity is 10, so we're going to say 800 here divided by 10, okay? So the mass is equal to 800 newtons, which is the weight, divided by 10. And so our mass here will be 80 kg. But listen now, they want us to find that on planet Y as well. Is that a problem? Absolutely not, because guess what happened now? The mass on planet X is the same thing on planet Y. Uh-oh. And do you remember why that is so? Do you remember why the mass on planet X is the same as mass on planet Y? Do you remember? Yeah? No? You should remember. All right. So the mass here, what's going on? Let me erase this one more time. All right. I don't know what is, maybe my hands. All right. So yes, the mass on planet X is the same thing as the mass on planet Y, because mass does not change. What changes is the weight. Okay, just remember that. So the mass will be the same thing on both planets. So you can make a statement right here that the mass will be the same on both planets. Okay? All right, I think this was a 2-mark question. All right, let's now jump to the next part. It's a give a reason for your answer. Oh, okay, yeah. So now we can answer it here for 1 mark. So we can simply say that mass does not change, right? The mass does not change. Mass remain the same. And I could tell you why mass remain the same, because that will be a good way to explain if you have a paper 3 or even if a paper 2 and they say explain why mass remain the same. All right, so mass remains the same. Mass remains the same regardless of location, right? And put this in regardless of location. But I want to tell you why mass of any object does not change regardless of where you go. It is simply because mass is a measure of the amount of matter or particles within that object. So no matter where you take that object, the same particles will be in it, which means the same mass. Okay? Or in other words, the same amount of matter is still in that object, regardless of where you take it. Right? And that is why mass remains the same. Okay? That's the sole purpose, or the sole reason, I should say. Simply because the number of particles or the amount of matter in that object is the same thing. So if I have a piece of box, for example, let's draw this box here. And this box is made up of, say, 1, 2, 3, 4 particles. No matter where you take this box, the 4 particles will be in it. The only difference is the amount of gravity that is acting on the object. So if I have the same box, regardless of location, with the same 4 particles, all right, they're not drawn to scale, okay? The difference is what is acting on the box, yeah? One may have a gravity, like example for Earth, which is 10 Newton per kilogram. This one may be 1.6, for example, Mars, and so on, right? That's the only difference. The difference is simply the gravitational force. All right, anyway, we can jump on from that, all right? I really want to finish this thing really quickly, because again, I'm against time, but I'm just get excited in explaining that, so forgive me. Let's look at this part right here, right? It's an object of mass 100 grams, right? So this mass here is 100 grams. Travels with a uniform acceleration, 2 meters per second. So we understand that this is a mass right here. This is acceleration. Let me kind of highlight them. So mass is 100 grams. I don't know why these lines are doing like this. Okay. All right, great. Now again, the acceleration here is 2 meters per second squared. Okay. It's a calculated net force on the object. Force, again, is mass times acceleration. I'm seeing this equation or formula for so many different times. So force is equal to mass times acceleration. Remember that? And so we're going to multiply our mass by the acceleration. But I want to notice something here. This mass is in grams. We need to convert this in kilograms. So we're going to divide 100 by 1,000. And so our mass here will be 100 over 1,000. I could put that real quick. 100 over 1,000. Okay. And this will give us, put the 1,000 real quick. This will give us 0.1 kg. So this is equal to 0.1 kg. Okay. 0.1 kilograms. All right. All right. Great. Now, so we can calculate now our force. And so our force now will be mass times acceleration. So F is our force, okay, equal to mass. Let's not put mass. Let's put 0.1 multiply by our acceleration, which is 2.0, no matter, just say 2. So this here will give us a value of 0.2 meters per second squared. Okay, so this is 2 meters per second squared. All right, so that will be our, let me take that out. That's not the proper unit here. Let me just delete this real quick. All right, so this is Newton. We're calculating force. All right, I need to slow down for real. All right, so let me take this out real quick. All right, so this is going to be Newton. So this is force. Okay, so Newton. Or it could be kilogram. It could be kilograms meter per second square as well. Okay, just to point it out as well. Because remember, we established that weight is also kilogram meters per second squared. All right, but Newton is sufficient, so that is great. All right. let's go to the next question right here now. It said the formula that was used to answer B1 came from what law? So in other words, the law that deals with force is equal to mass times acceleration comes from whose law? And this one is Newton's second law of motion. So this is Newton's second law of motion, right? Second law of motion. Okay. Now, what this law state? Anybody remember what this law state? It said that the rate of change of momentum, is directly proportional to its force. Okay. So what it's saying. So, a matter of fact, let me kind of explain this law for you a little bit, right? I'm not sure if you're going to see this, but if you should need to explain this law, let me just do it real quick. And this is a law. It said that the rate of change of momentum, okay, is directly proportional, let me say proportional to force. All right. So in other words, it's saying that force and momentum, they are equal, right? But let me show you something how this work out real quick. The rate of change, so the rate of change of momentum is directly proportional to force. So in other words, what this is simply saying to us now, right? Momentum, let's call this momentum, right? Momentum, which is mass times velocity, right? That's what it's saying. And it's saying that the rate of change of this, the rate of change of mass times velocity is equivalent to force. So in other words, this is saying now that mass times velocity, so what we have before there is momentum. So mass times velocity over time is equal to force, right? So it's equal to force. That's what this is saying. Because the rate of change of momentum, which means the rate of momentum, which is time, momentum divided by time, is equal to force. But let's look at something here real quick, yeah? Mass is kg, right? And then this now, velocity is meters per second. So what you get as a result here, you'll get our mass times acceleration, because velocity, let me just kind of circle this piece to show you exactly what I'm talking about. Because I want you to see where I'm coming from. Now, if I should take this piece out, let me just use this. If I should take this piece out, velocity over time, that is acceleration, right? So velocity over time is acceleration. Let's put A, correct? And M is mass. So I could still say that force is equal to mass times what? Acceleration. Because V over T is acceleration. Okay, so this is how this formula unit come from. The rate of change of momentum is the same as saying mass times acceleration, right? Okay, great. All right, so that's what it is. Let's jump to the next question right here. Question number 7. We're almost there. Almost there. Now, but question number 7, right? It said that this question is about sound waves. It says sound waves emitted by whales can be used for hunting, navigating, and communication. The frequency of these sound waves is within the hearing range of humans, okay? And it said, no, figure 7.1 shows such wave emitted by a whale and reflected upon reaching its prey. It takes 1.2 seconds. Let me point this out, because when I see these numbers, I want to point them out. It takes 1.2 seconds, which is the time, for the reflected sound called echo to received by the whale. Okay, so let's go and analyze this. So the time that the sound takes to go to the whale and come back, go to the prey and come back, is 1.2 seconds, yes? So bear it in mind. And then now, here it state now that state one property that remains the same and one property that changes after reflection of the sound waves. So when sound waves reflect, what change and what remain the same? So what remain the same is a number of things, and what changes probably only one little small things. So here now, remember this, the wave is coming from the same source. So first I'm going to point out that the frequency remain the same. Okay? The frequency is the same, coming from the same source. The wave is in the same medium, so no refraction is taking place. There's no refraction taking place, so there's no slowing down of the wave. So the wave now will have the same wavelength. So we can have frequency, we could have wavelength. So wavelength is the same thing. And also, if the wavelength and frequency are the same, then the speed must be the same. All right? So what changes then is just the direction. Right? Going back in a different direction, isn't it? So the direction no change. That's the only thing that changes. The direction. Now for part B now is a state a possible frequency for a sound wave emitted by the whale. Now the frequency says is within human hearing. So anywhere from 20, right, from 20 hertz, right, to anywhere about 20,000 hertz, okay, that is where we can hear things. So the whale will emit a frequency anywhere between these two numbers. If you state any number between these numbers, let's say for example 10,000, you're safe. Okay, you can also put this in kilohertz if you want. Okay, this could be 20 kilohertz if you want. All right, but just state it as that. All right. Now say bats can emit sound waves of frequency above human hearing. Okay, above the hearing of or the hearing range of humans. It's a given name of this type of sound. Anything above 20,000 hertz, we call that ultrasound. Okay, so it's called ultrasound. Okay, all right. So that's the sound that is called right there, that emitted by bats. If above the human hearing, it's called ultrasound. All right. Next part of the question right here now is given that the speed of sound waves in the ocean is 1,500 meters per second, how far away is the whale from the fish? Now they only give us time and they give us no speed. So time and speed now can help us a bit to calculate this thing because we want to find distance, right? But I want to point out something here for you though. There are two ways you could do this. As I explained in the graph, matter of fact, I don't need to go back today. I could go back to the diagram. I don't need to go back, but I could go back. I could draw a next diagram, show you, but maybe it's easier for you to understand from this. Again, if the whale release a sound, right, and it goes to the prey, the sound will have to bounce back, which is reflecting back to the whale for the whale to hear. If the entire thing, see, so it takes 1.2 seconds for the reflected sound, right, this is called echo, to receive by the whale. So the sound leaving the whale to come back to the whale for the whale to hear it, that's 1.2 seconds. The whole thing is 1.2 seconds, right? So what I want to point out now is that if you want to find the distance between the whale and the prey, just between the whale and the prey, you only need half of that time. Or you can do another thing. You can find the whole thing, then divide by 2. All right, so we can do two ways. One, you can divide the time by 2 and then do your calculations. Or you can do the whole thing, then divide by 2. So let's look at this now. We already know that distance, I want to find how far, which is distance. We know that distance here, well, let's say from this formula, velocity is equal to distance over time, right? So therefore, to find distance now, let's put it over this side, right? Distance is equal to v times t, right? Okay, v times t. So we already have a time, as is mentioned, which is 1.2. We can do, a matter of fact, I said we could divide the time here by 2 first, or we could do the whole thing, find the whole distance, and then divide the distance by 2, whichever way you choose, not a problem. All right, so if you want to go ahead now, I'm going to find the time in half first. Again, it really don't matter. All right, and so here I'm going to simply say time divided by 2. All right, so I'm going to say 1.2 divided by 2. Okay, which give us here this 0.6 seconds, right? So that's the time it takes only for one journey from between the whale and the prey. So now we have a time, now we have a speed, we can find distance. So distance here now is equal to v times t. So going to be 1,500. Okay, multiply by time, which is 0.6. Okay. And so here we'll have now equals to, that's 900 meters. So the fish is 900 meters away from the whale, okay? Again, you can do the whole thing by saying, okay, 1,500 multiplied by 1.2, you get 1,800, and then divide by 2, we get 900. The same way, okay? Not a problem. All right, so part 2 here now. Let's go to part 2. It said, what is the total distance traveled by the sound wave in producing the echo, the total distance. Now we go back to the total distance again. Now the total distance, you could do one of two things. You can calculate the distance between the whale, back to the whale, just multiply the distance by 2, or simply you can do you can do two things. Multiply the 900 by 2, or you can just simply say 1.2 multiplied by the entire distance, which is 1,500, and that will give us 1,800 meters. Okay. Again, you could just simply multiply the 900 by 2. Same thing. All right. All right. So now we established that. It says state one medical use and one industrial use of the phenomenon of reflection of sound waves. So how can we use sound waves in the medical field? And again, we can use this as ultrasound. You can use ultrasound in it. So ultrasound is not the answer really. Ultrasound is an application to what I'm going to talk about. So you can use ultrasound, okay? As a matter of fact, we also call the procedure ultrasound as well. So I guess it could work. So ultrasound scanning, I'm going to say ultrasound scanning, okay? Scanning, I'm going to give you an example. And we also know this way, so you're going to go to the doctor to do an ultrasound. Who normally go to the doctor to do an ultrasound is pregnant females, right? And say, so this could be used to scan fetus, okay? Use a scan fetus, all right? Use a scan fetus of pregnant mothers or pregnant ladies, right? All right. All right, so great. All right, so use a scan fetus during pregnancy. Let's put during pregnancy. Let's make this little sound better. Okay, during pregnancy. All right, during pregnancy. All right, so great. All right, so industrial use. There are many uses for this in industry. Many applications here. We could have one generally for cleaning, and the cleaning method here is ultrasonic waves. You could use ultrasonic to clean, ultrasonic cleaning. You can use for welding. In terms of doing welding, it's also important to do welding as well. There are special types of welding techniques to use that. You can use to also detect flaws in cuts, to detect flaws, especially in when you cut metals and so on. Detect flaws in cut, and not just only cut, even special type of cuts. You can give you a certain pattern, and so you know that okay, the cuts are not properly done. All right, and also you can use it for sound navigation. That's a good one. Sound navigation, to navigate by sound. All right, and I have a personal experience that I've seen this work with, is to locate fish. So like fishing boats, you can use it to find fish during fishing, yeah, or to locate fish. Okay, so locate fish. All right, so fishermen can use this to locate the amount of fish, or possibly approximate amount of fish in a possible area, and so on. Okay, yeah, so you can use it to do a number of things. All right, last question. Yes, and I'm very happy because I really need to go now. And so question number 8 now, we said 23892. This is uranium. Is a radioactive isotopes of uranium, decays by alpha particle emission and has a half-life. So I must highlight this. The half-life here is 4.5 times 10 to the 9 years. Oh Lord, that's a long time. All right. And then now it decays into radioactive isotopes, thorium, and thorium itself is radioactive and decay by a beta particle emission, all right, to produce protactinium. And this now has a half-life of 24 days. That's a short time. Okay, great. So it said now define half-life. Let's define half-life really quick. Okay, so half-life is the time taken. So this is the time taken for a substance, okay, for a substance, nucleus or mass. Let's say nucleus. For a substance, is nucleus or mass. Let me say mass. To disintegrate or decay, to disintegrate or decay, okay, to half. All right, decay or breakdown to half. Okay, they break down to half. The time taken to break down to half, that's half-life. All right, so the next part of the question now said, given 100 grams of the two isotopes, which one will have the largest mass after 2 years? And again, the uranium takes a very long time to break down. Notice the half-life here is 4.5 times 10 to the minus, 10 is 4.5 times 10 to the 9 years. So the half-life is very, very long. You have a very long half-life. It's going to take a very long time to break down. So here is going to be uranium. And since uranium, and this is simply because, again, it has a long half-life, or it takes a very long time. So it takes a very long time, or relatively long time, okay, long time, for half of the substance, half of the substance, of, I must say half of it, okay, of it to break down. Okay, they take a very long time for half of it to break down compared to thorium. Okay, so thorium only have 24 days. Okay, all right, and this one take a number of years. All right, so that will be your answer right there. It's a give one property of alpha particle and one property of beta particle. Okay, so I'm gonna give you more than one properties. So alpha particle is a positive charge, so this is positive. Okay, this is positive charge, the positive charge particle. Matter of fact, it's the strongest ionizing particle, so it is strong ionizing, so ionizing power is strong. So I'm going to say strong ionizing property or power. Okay, there's also another property for it, is that it has a weak penetrating power. So weak penetrating power. I'm not sure, you're not going to hold right here, but weak penetrating power. Let me just, I wonder if I could write that in. All right, just remember that. That's have a weak penetrating power. And so here for beta, it is negatively charged. So it is negatively charged. Okay. And it is moderate in terms of ionizing power. So you have a moderate ionizing power. All right. All right. And again, in terms of penetrating power, it has a moderate penetrating power. Okay. And here's a give one use of a beta particle. And beta particle can use to measure paper. So it can use to measure the thickness of paper. So measure paper thickness. Okay. All right. It can also be used in terms of cancer treatment to kill cancer cells. Or in some cancer treatment, not all, but cancer treatment as well. Okay. So cancer treatment. I'm just giving you some extra information here. You can also use as tracers as well. We talked about tracers in a previous question. So you can also use as tracers. All right, so we are at the next part of the question, part F. This is the last part of the question. Now we see that 10 marks. All right, so copy and complete the radioactive decay equation below for uranium decaying to thorium and thorium to decaying to protactinium. And so here now, the mass number, I want to look here closer to the mass number right here, right? The mass number in the product must be the same as the mass number in the reactant. So if this is 238 and this is 234, then this here must be 4, because 4 plus 234 give you 238. And then here you have 92, and 92 will come down to 90. That means this must be 2, because 90 plus 2 gives us what? 2. So this answer here is going to be 2. I'll put it a little bit lower so you don't mix up with the top one. For this now we have 234. All right. There's 90 here. There's no number given here. So here I'm gonna put 0 because there's no mass in the beta right here. So I'm gonna put 0. And then I'm gonna put below here now a -1. So I'm gonna put -1 right here. Okay. And so let's figure this out now. because we know beta, so we're going to put this here. So if there's no change in mass right here, we're going to put here is 234. So 234, no change in mass. And then at the bottom here, we have 90. So 90 here, we're going to put 91 because 91 plus a negative 1 will give us 90, all right? So that's there, very important there. All right. And so one thing I want to point out to you as well is that for the atom to change, the mass number is not that important, but the proton number must be different, right? Because if the same proton number, it therefore means the atom is the same thing. Because we identify atoms or elements based on the proton number, right? Or atomic number. I just point that out. Okay, so we're at the last of it. Again, it was a pleasure. Do well on the examination. Please, just focus. Take it easy. Drink a lot of water. Sleep well. See you next time.